All right. So yeah, this is a talk. This is something I'm actually really excited about and passionate about. And thank you for the invitation to speak again, Dr. Bosman. How do you solve a problem like infinity? I really like catchy titles, so this is a fun one. And now everyone's going to be singing a song in their heads throughout. First, a brief just sort of introduction to what I'm going to be talking about. This is more of a historical talk, but it's done by a mathematician. So because of that, it's a little bit, there's a level of informality to this. There's kind of a general level of informality in general. And so because of that, one second, just double check something. So because of that, that's just kind of the disclaimer for this talk to kind of give you the idea. So there is sort of a level of informality here. I've tried to consider put dates in as much as possible. The reference material isn't like hard reference throughout the talk, but at the very end, I give a list of references and further reading that I kind of use to compile all this outside of just having taught a lot of courses and kind of picked up things here and there. Okay. So yeah, with that said, let's begin. So first, as sort of the overview of my talk, I'm going to kind of go through 4 different phases of history. The first one is going to be kind of ancient, how the ancients kind of saw this problem of infinity and how it kind of arose. Then I'm going to talk about something that I got from, there was a book I read a few years back that talked about sort of the war on infinitesimals and what sort of happened with that. And so that'll be sort of the second part of the talk. The third part will be going from, I think is a really good piece because I think a lot of people aren't as familiar with it. If you've ever taken a calculus course and a real analysis course, you kind of wonder, how did we get to real analysis from calculus, especially if you're more in the sciences, but you've had both those treatments. So part 3 will be a bit about that. And then finally, part 4 is more modern results from the past couple of, about the past 200 years. So let's go ahead and begin. First, some questions to keep you up at night that some of you have probably asked yourselves many, many, many times, and others have not. What is the largest number you know? If you're like me, the largest number you know is kind of a hard thing to say because you always think, oh, well, I could just add 1 to it, right? And then ask yourself, sort of, well, how close is that number to infinity? Next, the second, in a like fashion, you could ask yourself, what is the smallest positive non-zero number you know? Okay, so how close to 0 can you get? And namely, again, how near to 0 is it? I like these 2 questions. These are usually 2 questions that, at least implicitly, I pose to my calculus students in their first semester. And I think it's enlightening to see that these are 2 sides of the same coin in a way. Another natural question to ask yourself is infinity a number? And we will hopefully sort of answer that question again, sort of implicitly throughout this talk. And then this naturally leads you to the question, well, why is 0 considered a number then, if infinity is not a number? Or maybe infinity is a number. Maybe they're both numbers, right? This is probably my favorite question here, which is if you were to try to come up with a definition for the term infinite, what would it be for you? If you weren't to try to go search through a textbook or anything, if you yourself were to come up with a definition of the infinite, what would it be? And also, back before, when you talked about, when we asked the question, how close is that number to infinity and how near is 0, and how near is that small number to 0, what did you actually mean by the terms close and near? So these are sort of the big questions, and these really are the big questions historically that have been the problems with talking about infinity is these sort of big questions. Also a bit of motivation for this talk, which is why should we talk about infinity? The joke is that it's a new semester full of infinite possibility, perhaps, right? So maybe we can learn more what that means. But more seriously, infinity stretches the human mind, and it's also central to our conception of what is and is not a number, which was sort of alluded to in the questions on the last slide. But a really big reason, this is one of the biggest focuses of this talk, is the history of considering infinity is actually full of a lot of disagreements, which gave way to really big mathematical breakthroughs and eventually some common understanding in the mathematics community, even though it did take a while. And I believe that we can learn a lot from this given where we currently are in our history. But then I say sort of the real reason. Well, the real reason is my research interests lie in harmonic analysis, which it brings up the question, what is harmonic analysis? The short answer is an extension of Fourier analysis, which this is a bad answer because it gives you another question, which is what is Fourier analysis? Fourier analysis, if you're unfamiliar with it, is concerned with studying problems related to Fourier series, which are basically like power series, but with sines and cosines. So instead of considering like trying to approximate with polynomials, you try to approximate with sines and cosines. Naturally, I'm not going to get super involved into it, but there is if you stop and think about trig functions, you say, well, that's kind of bad, right? Because they're all periodic. And the answer is yes, you are absolutely right. But much like power series, there's more implicitly this idea of like range of convergence. And with Fourier series, you don't expect it to converge everywhere, but you at least expect it to converge. Really, you can get sort of perfect approximations. That's the word I always use for convergence. You get perfect approximations on certain intervals, and it actually works really nicely. In some ways, it actually works a little bit better than power series. Physically, if you need some physical motivation for this, this takes the form of signal processing and electronics due to the superposition of the sine and cosine waves involved. More mathematically, as I said, it provides an alternative way to represent functions instead of using polynomials. In general, the best definition of what analysis is it's the study of infinite processes, most notably limiting processes, though it doesn't have to stay in that realm. So, and we'll see some examples near the end of kind of more broadly speaking, besides just limiting processes. And so in a sense, one way you could explain analysis, this is a huge oversimplification, is it's kind of like the study of the infinite, but the more mathematically rigorous study of the infinite. And then, so if I was to paint with really broad strokes, the way I usually explain to students is that if algebra is meant to be sort of abstract arithmetic and topology is meant to be abstract geometry, then I suppose analysis is abstract calculus. Or a lot of times students will be like, well, it's where you prove calculus. So I guess it's proofy calculus in a sense. All right, this finally begins our story. So our story, historically, is going to begin in the 6th century BCE. If you know anything about this time, this is a very, very exciting time in world history, especially for learning. This is the time period of Daniel, of the prophet Daniel. Some historical, like especially biblical history. Babylon overthrows Nineveh in 612 BC and defeats the Egyptian armies in 605 BC, which thus made, before I talk about the next bullet point, which thus made Babylon, during that time period until 539 BC, Babylon is considered the world is sort of the big world power, okay, at the time. And by world power, we mean, of course, Mesopotamian, Mediterranean, Egyptian area at this time period. Around 539 BC, the writing on the wall, the writing is on the wall for Babylon, pun intended. The Persians come in. The temple is rebuilt in Jerusalem by the end of the century due to Cyrus's proclamation. And meanwhile, over in the Mediterranean, civilization is finally starting to ramp up. So what do I mean by civilization is ramping up while this is happening? So first, a bit of a disclaimer. Until Plato in the 4th century BC, there is virtually no mathematical or scientific records in existence. So we kind of have to take things that were passed down to when people could actually write it. So think sort of the world history equivalent of the mathematical, I should say, history equivalent of the book of Genesis. So things had to be sort of passed down. And so a lot of this stuff, it's like, well, this is what everyone says, and everyone seems to agree that this is what happened. So I guess this is what happened. So from 800 BC to 800 AD, this is known as the Thalassic, as in sea age of civilization, due to learning being focused around the Mediterranean, mostly due to the Hellenistic learning with the Greeks and the Roman Empire. Around 600 BCE, so around the time that Babylon has become the sort of the sole world power and the dominant world power, mathematical knowledge actually began to thrive in Greece, thanks in large part to two very important men, Thales of, I'm not even going to try to pronounce that, and Pythagoras. Most of you have heard of Pythagoras, but these two men were very important for a number of reasons, but one of the big reasons was that they actually had the means to travel and to learn from others and then kind of collect that information. So Thales, a bit about him before we dive into Pythagoras, who's the really interesting person we want to focus on. Thales has been called the first mathematician by some commentators. However, so legend has it that he actually predicted a solar eclipse and amazed everyone in 585 BC. He may have done this because he was able to travel and gain the astronomical knowledge that the Chaldeans had ascertained and put together. He's also been credited with logical deductive elements, which are central later on in history to Euclid's Elements. So he was kind of he's been given credit, and later mathematicians gave him credit for being one of the first to be able to do this sort of logical deductive process. So meanwhile, Pythagoras and his followers were an interesting bunch. Something that perhaps you never realized is that Pythagoras and Daniel are actually contemporaries. They actually lived in different areas of the world. So they probably, I mean, it's possible Pythagoras and Daniel may have saw each other in passing, you know, in sort of wise men circles as Pythagoras was traveling. But otherwise, we have no reason to think that they actually ran into each other. But also Confucius and Buddha were actually were alive at the same time period. So it's an interesting time in world history, right? You got all these sort of major ideas happening all at the same time. Upon returning to the Mediterranean, Pythagoras actually founded a sort of cult in the area of Croton on the southeast coast of modern Italy. This group, which we now know today and were later known as the Pythagoreans, they were communal, so they were very community focused, they were very secretive, and they were characterized by understanding pretty much everything: philosophy, cosmology, morality, everything in terms of mathematics. They thought everything was to do with mathematics. In fact, the big theme of the Pythagorean worldview was all is number. A good example of this is Pythagoras's table of opposites. Here you sort of have, in the one column, you have the good, the finite, the male, the odd, the right. And then you sort of have, on the other column, the evil, the infinite, the female, the even, and the left, okay? And it's interesting because they would typically kind of categorize these two. Some of these don't really make sense or are even kind of offensive, right? I mean, by today's viewpoint. But one that is interesting to me, that's for some reason, as soon as I saw it, I was like, that makes total sense, is that odd numbers should be male and even numbers should be female. I don't know why that makes sense in my mind, but somehow that makes sense to me. So I think it has something to do with X, Y, and XX, and there's two X's, so, and that's even, but anyways. As a note here, so sometimes you've probably seen the Pythagorean theorem be called Pythagoras's theorem. The reason for this is it was very customary to group things. It was, oh, sorry, I'm jumping ahead. But yeah, as I said, it was customary to group things in the same column. But as I was saying, yeah, that it was customary for Pythagoras' followers to give all credit to him for discoveries they made. And again, it was part of sort of that communal living, right? It was this idea of like, well, Pythagoras came up with this worldview. It's all really because of Pythagoras. They also had a tradition of placing arithmetic, that is numbers, as of higher importance than geometry, which would have been like measurement of lengths to them. This is surprising. It's thus surprising that in addition to the theorem that which probably mistakenly got their name, because the Pythagorean theorem was actually known to the Babylonians, but also they were highly concerned with construction of pentagrams, which I feel like that kind of finishes off the whole cultic like view of these people, right? Is that they're really interested in constructing pentagrams. So, and here's a picture of one of the few pictures of these ancient philosophers that I included. This is a picture of Pythagoras, because you know you can see the Pythagorean theorem demonstrated down there too. So one of the big, this is our first. So throughout this talk, we're going to see a number of debates that arise through all of it, and the conception of the infinite. And one of the more interesting Pythagorean beliefs was that since all is number, it followed to them that all numbers and lengths, that also means lengths, they should be written as whole numbers, okay? Now you say, well, that's silly, right? Of course there's fractions. Well, that's not the way they thought about things. They didn't really think of fractions because their idea is really, so from a modern viewpoint, this means the same thing as everything being rational, because they can be written as fractions. Their idea of fractions was really they could change fractions into whole numbers by scaling appropriately. So the idea was, if you had like, I mean, we see this in geometry still, right? Like we know that if you scale a 45, 45, 90 triangle, then it just changes. It changes the lengths, but they all stay in proportion to each other. Well, why not write 1, 1, root 2 for the side lengths instead of writing 1 half, 1 half, root, or root 3 of root 2 over 2, right? So that was sort of their viewpoint on things. And so they really liked whole numbers. And that's a really great worldview and stuff. But of course, as a historical irony, as I just alluded to, the one result that still bears the Pythagorean name gives a counterexample to this viewpoint. So namely, of course, if you have a right triangle, you know that the lengths of the sides, if you square each of those lengths and add them, you get the length of the hypotenuse squared, okay? And here's the 45, 45, 90 triangle I talked about before. This is the proof. If you've never seen it before, it's a wonderful proof. I know my students have seen it before, that the square root of one way to show that you can create irrational numbers from the using the Pythagorean theorem. So suppose you had a right triangle and you have to visualize in your mind. You have a right triangle with sides of equal lengths, which are S, and a diagonal of length D. Assume that D over S is rational, that the actual, that the ratio of the sides creates a rational number. Then there should exist positive whole numbers P and Q such that you can write it in terms of the ratio of P and Q, right? By the Pythagorean theorem, we know that we know that thus d squared would equal 2s squared, okay, because it's s squared plus s squared. If you go through and you use some algebra, you'll eventually end up with a statement that p squared is 2 times q squared, which means p squared is even by definition. Well, then it follows that p must also be even. When you know that you have an integer and its square is even, then the integer itself had to be even to begin with. Again, that's a fun thing I do with my intro to proof students. Thus, you can write p as 2 times some positive whole number. Going through this again, you're able to derive that q squared is equal to 2 r. That should be r squared, not r to the s. Sorry about that. So similar to before, q squared is even, and thus so is q. However, this then causes a contradiction. The contradiction is that we know that we can reduce p over q by canceling a 2 in the numerator and denominator. And you say, well, why is that a contradiction? Maybe you just wrote your fraction poorly. Well, the problem is that it doesn't matter which fraction you chose, though, p over q. So somehow we created a fraction that we could always reduce. And that's the contradiction, is you have this forever reducible fraction. So in other words, it's d over s is in fact incommensurable, which by our modern definition means it's irrational. There is a legend that goes along with this, which is that a Pythagorean named Hippasus actually discovered this, possibly by the same argument, but he may have discovered it with the pentagram, because the pentagram also does this, also creates similar problems with square root of 5. And when he learned this, the legend goes he was mysteriously lost at sea. So he just sort of was taken care of by the Pythagoreans. So that's sort of a weird, shifty piece of history, right? There's a few other problems with all this number. One that's pretty obvious to us now is that if you do rational incommensurability challenges the idea of an atomic structure of the real number line, which seemed to be what they were operating under. And it's pretty easy to see why. Namely, A and B are, if you have any two numbers, A and B, you know that are different from each other, with A less than B, then you know that you can always squeeze a third number in between them, which is the average, right? And more importantly, if A and B were rational to begin with, so is the average, which means that between any two distinct rational numbers, there's not just one other rational number, but you could keep going with this, right? You could squeeze another one there and there, so now you have 3 in between there, and in each of those gaps, you could squeeze more, and you could just keep going with this. There we go. However, an even more blatant challenge to the Pythagorean worldview was a focus on geometry over algebra, which was really what they, and by algebra I mean really arithmetic in this point, which pervaded other philosophical movements, most notably I think the term is Eleatics, the way to pronounce that, who believed in unity and permanence, which was a direct challenge to the Pythagorean tenets of multiplicity and change. Well, guess who was an Eleatic? Zeno was. And if you know anything about Zeno, you know that he proposed several arguments showing the inconsistency in the concepts of multiplicity and change. He had 4 big ones that seemed to cause the most trouble for the Greeks, just across the board, not just the Pythagoreans, but for all of the Greeks in general. They struggled with these paradoxes. There's the arrow paradox, the Achilles paradox, the dichotomy paradox, and the Stada paradox. The arrow paradox can basically be summarized with this image. It's the idea that if you shoot an arrow, it has to go first half the length, then a fourth of the length, then an eighth of the length, and basically it has all of these stopping points. Well, it seems like it has an infinite number of lengths that it has to go through before it can ever hit a target. So how does it ever hit a target? Because it should still be going through them because there's an infinite number of them. The other paradoxes are similar to this. Let's say we have a rabbit named Achilles. originally it was Achilles, like the runner. But here, let's say we have a rabbit named Achilles, and it's the tortoise and the hare. Well, the tortoise, let's say, starts ahead of the hare. Well, by the time the hare gets to where the tortoise was, the tortoise has moved, even a little bit. Well, by the time the hare gets to that point, the tortoise has moved again. And by the time the hare gets to that point, the tortoise has still moved again. So does the hare ever catch the tortoise? It seems like no, right? It seems like the tortoise is always going to be a little bit ahead of the hare. The dichotomy paradox was basically, and I'm not going to do the fourth paradox, it's a little hard to state, but the dichotomy paradox basically is sort of the reverse of the arrow paradox. It kind of makes the argument that similar to how an arrow never seems to reach its target, it's a miracle that we ever start moving, which is, in order to start moving, we'd have to go, in order to cover one whole unit, we'd have to cover half, but then that means we'd have to cover a fourth before we could do that, which means we'd have to cover an eighth before we could do that. And it seems like we have all these infinite numbers of distances we'd have to cover, and so do we ever even move? And each of these paradoxes describes a problem with our concept of motion, as you can see. And if you know anything about calculus, you know that each one has a similar resolution with calculus, and that we now understand now they're not really paradoxes and once you sort of get your ducks in a row. So a bit of course correction. By the time Zeno, because of Zeno's paradoxes, very few people wanted to consider infinity. A few dabbled in it, though. Eudoxus came up with a definition of ratio, which is actually very similar to our modern understanding, which is, well, our modern understanding of two fractions being equal is that they can cross multiply and that those are the same then. His definition was a bit more technical, though, in that it used integers m and n to kind of work out the equations and inequalities stemming from reducing the fractions. It is not too dissimilar from how we define real numbers, though, as it effectively separates the rational numbers into classes, okay? So think, if you know what Dedekind cuts are, that's what it is. Is essentially, this is the way we view our construction of them. One way to construct the real numbers is to break up into equivalence classes of sets and basically create cuts, so to speak, in the real number line. This also forced the Greeks to contend with that which they did not want to, which was an infinite set. Eudoxus' big idea was was to create something called the method of exhaustion, which is the comparison of curved and straight line configurations. Namely, if you think a modern day integral, that's essentially what he did. He had a method to integrate without integrating. The key tool in this is the following lemma, which is given two magnitudes having a positive ratio, we can always find a multiple of either one which will exceed the other. This is really what we now know today as the Archimedean principle, okay? And it is foundational to any understanding of how to create a limit, all right? The limit definition is very central to the Archimedean principle is sort of the groundwork for the limiting process. So this led to what is called the method of exhaustion. If you want the modern statement using quantifiers, a more modern statement of it, and it also appeared in Euclid's Elements, is that for any positive numbers and r as a number greater than or equal to 1/2, but still less than 1, you can always find an integer n such that m times 1 minus r to the n is less than epsilon for all positive number integers, lowercase n greater than positive n. What we would write that today is that that's a limit that equals 0. That's how we would write it now, because it's an epsilon delta definition. However, as crazy as it seems, limits were still a couple millennia, yes, you heard me, not centuries, millennia away from being the modern day form that we understand today. So things took a while to get moving. There's a joke here if you know your history, but I'll leave it there. To demonstrate the power of the method of exhaustion, consider Euclid's uses of the version of it in the Elements to prove that the area of a circle is pi r squared. This also gives us one of our modern day ways that we tend to approximate pi, which is by circumscribing circumscribing and inscribing polygons, and then slowly upping the number of sides. And the nice thing about this is that you really only need the method of exhaustion, that one particular limit, to be able to figure this out. And so that was kind of nice. So they toyed with calculus. They got just a tiny bit of it, but that was about it. And otherwise, they were kind of scared away. So which brings us to the second part of our talk. And I am adjusting this for time, so you know, but I'm doing pretty well, actually. In 300 BCE, Euclid's Elements is published, which is the big, probably the most famous mathematical work in the history of man. I know many of you probably thought it was Stewart's calculus, but it's not. It's Euclid's Elements, which even though it used arguments using the method of exhaustion, it was very careful to avoid the explicit use of what we now know as infinitesimals. So infinitesimal is really something, by definition, it's a length which is closer to 0 than any other length. Well, based on what we've already done, what I showed you with the averages, and what I showed you first, with the average of any two rational numbers being rational in between them, you know, infinitesimals, logically speaking, are a fiction, right? They seem like they should be a fiction. And so due to Zeno's paradoxes, people were kind of aware of this, and so they were very scared to consider this, right? And so that was the idea, is they kind of avoided infinitesimals while still using the method of exhaustion, which basically used infinitesimals without using them. Even after Euclid's Elements, Archimedes seemed to still kind of take the method of exhaustion to its inevitable conclusion, which he did a lot of work playing around with infinitesimals. Again, this is going to be important for the next part of this talk, but in 1517, Martin Luther nails his 95 Theses to a church door in Wittenberg, okay? So it's a huge time skip now. We're moving into the 1600s coming up. And this officially kicks off the Protestant Reformation, and which leads to Catholicism losing a lot of the power it had had across Europe. While in 1540, Ignatius of Loyola founds the Society of Jesus, which we now know today as the Jesuits, and they were tasked with reviving Catholic doctrines and restoring church authority. And in 1544, to complete the picture of what's going on at this time, to create the perfect storm that's about to happen, in 1544, a Latin translation is published of Archimedes' work. This led to a revival of interest in infinitesimals throughout the 1600s, okay? So it's this perfect storm of things that are happening now, which is going to kick off the next big like battle in the war against infinity, okay? So one of the first in the Western world to, Christopher Clavius is sort of our first interesting character here. He was actually one of the first in the Western world to use decimal point to represent numbers. So that's kind of one of his claims to fame. He was a Jesuit who began teaching at the Collegio Romano in 1560. And in an effort to standardize daily life in a Catholic model, around this time, the Gregorian calendar was introduced, the same calendar we still use to this day, named after Pope Gregory. Clavius both worked on and defended this new calendar system to people. Well, it was only a matter of time that they did so many great things with the calendar that they thought, you know, it would be great, we will standardize mathematics. Let's standardize mathematics. So here you go, math reform. We all know how well this turns out, right? So he decides, I'm going to do some math reform with the Jesuits, and we're going to create our own mathematical tradition based only on Euclid's Elements, nothing else. Everything should be geometric, it should be ordered, it should be rigorous deductively, and now we'll have absolutely true results, and no one will be able to thwart us because of that. Well, the goal here was not mathematical innovation, as you can see. Rather, it was the application of what we already knew and to try to keep everything in that framework, right? And this is a theme we see throughout mathematics, okay? Even in modern day settings, there's this idea of, well, we want rigor, right? We want rigor. We want to be able to prove results, okay? I will say one of the interesting pieces of history is that mathematics is usually discovered. It's the concept is discovered and the rigor comes after usually. Things kind of turned on their head when set theory came around, where suddenly the rigor is what gave us the results. But that's a very modern invention now. Historically, it was much more of you've discovered something, and then later on, the mathematician would make it work out, basically. So this inevitably, as you can see, led to a war on infinitesimals within wherever the church's jurisdiction remained powerful. Well, Galileo was, he became an easy target of the Jesuits due to his advocacy for Copernicanism, because according to the Catholic model, of course, naturally, the earth is the center of the universe, right? The Bible even says the earth is the center of the universe, supposedly. And so, because of this, when he advocated that Copernicus was right, the sun is in the center of our solar system, this became a problem. And guess what methods he used to do this? Infinitesimals. So naturally, this bad mathematics is creating bad science, right? So we got to figure this out. Well, this starts leading to a war, a bit of a war on infinitesimals by Catholicism, and most notably the Jesuits. They denounce infinitesimals. I'm going to go through these historical points pretty quickly. The same year, Galileo is convicted of heresy by the Inquisition and sentenced to live out his life under house arrest. His disciple publishes in 1647, in 1635 and 1647. These actually become very standard works among the mathematics community across Europe of this method of indivisibles, which is infinitesimals. And it grows into its own sort of mathematical discipline at this time, okay? So this is a big deal, okay? This is like the, I'm trying to think of a good, this is like the Langlands, the Langlands project of its day, okay? The Langlands program, that's what it's called, of its day, if you know what that is, okay? So it's a big happening thing, it's exciting. Various other disciples of Cavalier and Galileo also published their own works throughout the 1600s. In response, the Jesuits published in 1651 banning all doctrines about infinitesimals. So if you use infinitesimals, you're out. Okay, as far as Catholicism is concerned, you're out. None of your stuff is to be taken seriously. It can't be taught in any of our schools. We're not having it. Most notably, this pretty much effectively killed mathematical progress in Italy. So there you go. Meanwhile, we have another story happening in England. All right. In England, from 1640 to 1660, a civil war between King Charles and Parliament leads to the former's execution in 1649. Thomas Hobbes flees England for Europe, flees England for mainland Europe, France, in 1640, as he is a staunch royalist in England. Today, it's not surprising then that today Hobbes is best known for Leviathan, which is a philosophical work where he advocates for a totalitarian state and how great it would be to have a totalitarian state, which if you know anything about Leviathan, it's the idea of like, no, the totalitarian leader is all of us, right? They represent all of us. So the king is all of us, really. He speaks for all of us, and we are all the king, and it's good for all of us together. Interestingly, he grounded a lot of his reasoning based on Euclid's geometry. Again, you're noticing a pattern here of, oh, it's so much great order, right? Math gives us so much order. Perhaps you've heard people say this. It gives us this great order. It's so wonderful. We should just ground everything in mathematics, right? Pythagoreans did it. It was wonderful. Jesuits did it. It's great, you know. And Thomas Hobbes, yes, this is a great idea. Well, meanwhile, back in England, John Wallis is ascending. He's a scientific man who's a major participant in private meetings, which later becomes the Royal Society of London. All right. He also becomes Oxford Professor of Geometry, ironically. And today we actually remember him in several calculus theorems as he was a leading infinitesimalist. You've possibly heard of Wallace's formula before. What followed was an ideological war between Wallace and Hobbes in England, which mirrored that of the Jesuits in Italy. It actually gets pretty nasty. I'll just go quickly through this. So Hobbes, shortly after, returns to England. Wallace publishes work where he's able to compute areas of conics and various other measurements in conics using infinitesimals. And some of these were already known using geometric means, but he's able to set up infinitesimals as actually a really great way to solve problems here, because it gives the same answer of the classic problems, but look, we can solve all these new problems too. That same year, Hobbes publishes and he publishes a proof of, wouldn't you love to have a proof of this, squaring the circle? Because as we all know now, it's impossible to square the circle. It's been shown that you can't square the circle. Well, so Hobbes publishes this, okay, and he publishes all these unresolved problems using geometry. You know, it's the guy who comes along and is like, I don't know why the Riemann hypothesis has been stumping people for, you know, over 200 years now. It's so simple. How did everyone miss this? Well, Wallace couldn't resist, and he ridicules Hobbes in publication by pointing out his mathematical mistakes. Hobbes returns back, talking about how all of Wallace's use of infinitesimals, that's a hard word to say, is nonsensical. It's going to create error, and it can't lead to truth. It's bad, right? This continues for years now until Hobbes finally dies, okay? And so you may be wondering who the winner is. You probably, if you know your history, you already know who the winner is, right? So Isaac Newton, I forgot to put the dates in clearly, experimented with infinitesimals so as to determine techniques for studying motion. Today we call this calculus. Leibniz, around the same time, published his own version of calculus. Hobbes dies in not 1979, 1679. I did a error there, being both mathematically discredited and politically isolated. Because by 1679, of course, people had calculus, and this was a thing now. Like the tide had the pendulum had swung, and he was on the wrong side of history. In 1703, however, Wallace dies, and he is viewed as a revolutionary, ahead of his time even. All right. As I'm running short on time, we'll go through a bit of this. If you know much about, Newton and Leibniz, you know that there's some contention there about who created calculus, and we now kind of realize that they both kind of came up with calculus and put and as you can see here, there was a big body of knowledge about infinitesimals at that point. Throughout Europe, everyone was doing this. This was the happening thing to be looking at, mathematically speaking. And so they probably just put together results at the same time. Newton was very concerned with laws of motion, so he was kind of continuing in the Galileo model of like, how can I use this to figure out the motions of the planets, you know? How can I use these calculus ideas, what became calculus? And Leibniz, meanwhile, seemed to just be shoring up more the mathematics involving infinitesimals and kind of streamlining the process. So a natural question is then, was Zeno wrong? Well, Zeno was right in that there's an infinitude in motion, but he was sort of wrong in the sense that this actually causes a contradiction. We now know today, thanks to wonderful, excellent calculus understanding, that you can solve at least all three of the Zeno's paradoxes I gave, you can solve using just geometric series, actually. So you don't even need a ton of calculus. You just need geometric series, okay? To realize, oh, well, yeah, here, we actually go a whole length of time. We just go, whatever those units are, it's one of that, okay? And it's easily done with geometric series. This does cause a few bigger problems, which is, why can we add some things, but why can we infinitely add sometimes, but not other times, right? Sometimes we get an answer, sometimes we don't get an answer. Here's my favorite proof of the the divergence of the harmonic series. You group the terms one at a time in pairs. You do a really generous estimate, which is you round one down to one half. You take one down to one half, 1/3 down to 1/4, 1/5 down to 1/6, and so on. And what you end up with is a copy of itself. So somehow it's greater than itself. Well, that's clearly a contradiction. So I guess it can't be a real number because otherwise it's some number that's greater than itself. An even worse example of this is a favorite proof that 1 is equal to 0. So we have problems with series, right? With adding up infinite number of times. There's even bigger problems with series though. For example, if you consider power series centered at, if you consider the power series for 1 over x centered at 1, you get this, this wonderful perfect approximation, as I say. But this leads to a lot of questions, which is, what does the equal sign mean here? When is the equation true? Is there a reliable way to derive such a series? How useful is such a representation? Can we even do calculus on it? Can we integrate it? Can we differentiate it? Can we go term by term? Which basically amounts to, if you put a derivative sign here, is it the same thing as putting a derivative sign on the inside? If you put an integral sign here, is it the same thing as putting an integral sign on the inside? Is this even continuous, right? Once you add it up, does it even become something continuous? Analysis is important to kind of to move towards wrapping this up. Analysis is great because it answers all these questions. Calculus does not. Calculus basically says, we can do things. Let's just do things. It'll work, right? Let's do things. Well, just because you can do it doesn't mean it's useful, right? And so analysis tries to answer a lot of these questions. So the story continues. A lot of these ideas came to a head, skipping ahead a bit, with Fourier series. This is why Fourier series is such a big deal. Fourier was trying to solve the heat equation. And he actually came up with the equation for heat, the partial differential equation that represents heat. But the breaking point kind of came with his solution method. His idea was to use what we now know as Fourier series, which is basically power series, but with trig functions instead, okay? The big issue here was he claimed that you can write any function this way. And when he says any function, he means any function, not just continuous functions. Discontinuous. He's like, yeah, any function can, which angered a lot of people. But part of it was it brought up all these questions before from earlier. And what he didn't realize was Fourier, let me go back. Fourier basically opened an old wound, which was all those questions I asked earlier about the power series, right? He had opened up this wound. This was an old wound by this point that lots of people had run into with series. And mathematicians, it was really bothering them. Well, let me summarize this by saying the good news is we do have infinite weirdness that works. This is how I describe working with infinity. We now know how to work with infinity in a way that works while we're also very wary of things. So this is this is a better way of this is the way I like to see the 1/4 plus 1/16. This is another geometric series, and that does actually converge to 1/3 of the whole figure, right? If you see that, you can kind of see that it's 1/3 of the whole figure. Also, another favorite of mine is you can use geometric series to show that 0.9 repeating is actually equal to 1. Which always bothers students, right? Because they're like, no, but it's just really close to 1. Well, how close is it? Well, it's infinitely close to 1. Okay, that sounds like equal to 1 to me. All right. This is where I go through a bunch of stuff. All really great stuff, but some final thoughts I wanted to share with you. Whenever you use a limit, you should remember that, 1, you were trying to create a definition for what infinity means. This is how I view limits. And 2, you were standing on the shoulders of giants who came before you, thousands of years worth of people. Sometimes it takes 100 people, hundreds of people, a few millennia to come up with the right idea. Other times it takes just one person in an instant, which, if I had been able to talk about it, Cantor basically revolutionized the whole modern idea of infinity with with finally understanding and creating a definition for what we meant by infinity. Very rarely are good ideas universally accepted in their time. History will be the judge. And if you really like infinity, do work in analysis. You will get to play with it a lot, most daily. Here's a few references / further reading if you'd like. I have the books here. If you like go over to my face, you can see here. So all really great books. And that's it. That's all I have.